Okay, so in this question, they say that we have a relay that regulates voltage of the current. The force in the spring CD, so you have to know exactly where the spring is. That's our spring, which has stiffness. So stiffness there, that is basically just the spring constant K, which is 120 Newton per meter. So that it will allow the armature to make contact at A that is here. And then in the first part, in the figure A, with a vertical force of that. So that is basically not in the first part, that's just basically figure A with a vertical force of 0.4 Newton. Also, determine the force in the spring. Okay, that's the second part now. Now, the key thing here is to understand exactly how this question works or how this relay works. If you can create a clear picture of how the relay works, you will know exactly how this diagram is going to work or how the whole concept is going to work. I think this is a concept that you have to develop or you have to try to master whenever you're dealing with machines here. You must know exactly which part is going to be moving, what makes that part move. If you can picture that, then you know exactly where the forces are going to be and how to actually find them. What do I mean? Well, for this relay, for example, you have to picture what happens when the circuit is complete, what happens here, when do we expect this to detach from here, and what happens, what causes it to detach, and so on. And the spring, what is its state? You must be able to predict the rest position of the spring. Do we have the rest position somewhere, maybe there? So that in this case, maybe the spring is already compressed to some degree. And then when the armature is pulled downwards, like in this orientation, then we have the spring stretching even further. So that maybe, just maybe, the rest position is somewhere here. You must have this figured out already before you start working out. And the only way you can know this very well is if you can picture this in the actual sense. Now, what happens? How do you know exactly what the state of the spring is? And here, by the state of the spring, you want to know if the spring in this current orientation, is the spring compressed or is it in tension, as in is it stretched? So that when it now comes in this state, then you're going to answer, is it compressed or is it in tension? Or maybe both, in both situations, the spring is in tension. Now, what helps you to answer those questions is exactly what they're saying here. In the first part, get this. They're saying so that it will allow the armature to make contact. So the armature makes contact at A with a vertical force of this. What is happening there? So in that case, we are seeing that the spring here allows the armature, meaning allows this, to bear down onto this armature or onto that contact at A with a force of 0.4 newtons. In that case, what is happening to the spring? So it's like you have something like this. This is that structure AB, or is that, let me get the labels. That's ABC. So you have this structure ABC. Okay, so that is our structure ABC. And at point C here, we have our spring. And then at point A here, we have that armature making contact with that end. Now, what we're saying here is that this point, the armature bears down onto that contact with a force of 0.4 newtons. What does that imply? It means that for this part here, we see a force that is going upwards, bearing down onto that contact. And that force is given as 0.4 newtons. Now, here I'm just trying to draw a free body diagram of everything that is happening here. At point B, you have this point here that looks, of course, if you picture this diagram very well, you have to see that all the rotations will be happening about that point. You can show the reaction forces there and say this is going to be some form of a support here, and this looking like a pin. You can even give it reactions to say it's going to have maybe a vertical reaction like this, a horizontal, I mean, and then it's going to have a vertical like that. Again, up to you, the orientation there. Then the last part is going to be what is happening here. In this case, what is going to be happening there? Well, that is where the spring now comes into the picture. There are two situations. Either the spring is pushing that point up or it's pushing that point down. But in this case, what we're going to see is that we're going to assume the spring is actually pulling this point downward there. Now, in making this assumption, what are we actually doing there? We are assuming, can you guess the state of the spring in this case? Is the spring, with my assumption here in red, is the spring in tension or compression? Can you guess? What do you expect for our spring? Okay. So the treatment of the spring here, when I was asking to say what is the state of the spring, when I assume the force on that beam ABC is it's a downward force, it implies something like our spring has actually been stretched already, such that it is trying to go back to its rest position. It's trying to more like compress a bit so that it goes back to its relaxed state. So it's the attempt of the spring to restore itself to its position that tries to cause this beam to swing in this orientation. As the spring is trying to go back to its rest position, it forces the other end here to rotate upwards like that, hence making contact at point A there. So the spring already here is trying to go back to its relaxed or equilibrium position. In other words, the spring is stretched in this case. So the rest position of the spring, we expect the rest position to be somewhere here. So already the spring is in tension. Now, that is just a description that you have to understand. We'll come back to what that implies in a few minutes, but for now, we can actually work out what the force in the spring is for this setup. In this case, to find the force in the spring, we are just going to evaluate moments about that point there. So we will do moments about this point so that we do not have to worry about those reaction forces at that point. Well, the best thing is, if you look at this diagram this side, we're given what the distances are. So if I'm taking moments here, for the force in the spring here, or the force at that point there, the horizontal distance will have to be a distance like this, so that it comes to be perpendicular to the line of action of our force there. In the same way, for the vertical force at point A there, the line of action is this. The distance that will be perpendicular will have to be a distance that comes up to here. So that distance is what we're going to use. And if you look at this diagram here, it actually does give us what those distances are. From point A to where that support is, that is this part, that distance has been given as 50 by 50. So for this part, we're going to have 120 by that's by what? We're going to have by 50, by 100, sorry, which is 50 plus 50. So I have 100 millimeters. But in this case, this is more like bearing down onto that contact at A. So you know to say what will show up really is not this upward force at this point. It's not necessarily that upward force that will show up. Since I have only isolated this structure, to this structure, what will actually appear here is not that, but it will be the reaction from the upper contact that will react to that force. Okay, this is moved. Okay, let me just take it back. Okay, so I was saying at that point, what will actually appear in our free body diagram should not be what the force or what the armature is exerting to that contact at A. Instead, it's the this comes to act as a support, creating a reaction that is equal to that 0.4, but now just bearing downwards like that. I am changing it to use that one for one simple reason. When this is in equilibrium, or when the armature is in contact at point A, that beam ABC will be in equilibrium, implying that the rotation that are trying to be caused by the restoring force in the spring will have to be equal to the rotation being caused by the reaction at that point A. So we want to equate the rotations there. So this is what brings the right-hand side to be the restoration force in the spring. I can say Fs to mean just the restoration force. And then, but here the distance will have to be from here up to here. What will be that distance? So that is from point B to point C, which is basically just this distance here. And that distance is given as 30 millimeters. I haven't bothered to convert the units for the distance because I know the units are going to cancel both sides. At this point, we can finish up this. The left side becomes 12,000 there. The right-hand side will just be 30 Fs. So that the restoration force here will end up being equals to 12,000 divided by 30. The 0 will be knocked out there. 3 into 12 is 4. We get 400 newtons. This was Newton per meter. So that is going to end up being, not Newton per meter, that was 0.4 that. Wait, why do I have the 20 here? You guys didn't correct that. This is not the 20. It's the force we're dealing with. So it's not 120 by 100. This is the force that the armature exerts on that point at A. It's not 120. That is 0.4. I don't know why I used that 120, but I hope you guys were able to see that. That is 0.4. So here we should have 0.4. So this will not be this. By this are going to get a 40. Okay, yeah, this is going to be a 40 there. So that this changes. So you guys should really pay attention. Don't let me make these silly mistakes. That should not be a mistake that we are supposed to make. This becomes 40 over 30. The 0 falls off. We end up with 4 over 3 as the restoring force, or the force in our spring at this state. Okay, any questions there? For this part, it's exactly the way we did it last night. I haven't yet made any adjustments yet. Like I said, we'll only see a difference at the very, very end. Now let's look at the second part. What do they want us to find? You first must have a clear picture of what is happening here. Our spring is stretched. It's because the spring is stretched. It's like initially the spring is something like this. It's like initially this is the state of the spring. When it's at rest, meaning at this point it is at rest in equilibrium, that as in just basically at rest, it's not in compression or it's not in tension. But when it is now connected to this structure, the spring gets to be stretched a little bit. It gets to be stretched. So this is what we are seeing. Because in this state, when it is connected, the spring is already stretched. You know, the spring, provided it doesn't exceed the elastic limit, it will always try to go back to its natural position, which is this state. So in other words, it is in tension. It will be exerting a force at this point, which will be a restoration force, and it will be a downward force. This is the force that we were finding. The spring itself is in tension, but it exerts that force on that beam there. That is the force that we have found there, that 4 over 3. But look at what happens. For this beam to now go horizontal, what happens? For the beam to go horizontal about this point, it now implies that this beam or this point at the far end must now be dragged downwards. When you drag that point downwards, what happens to the point in contact with the spring? It must go up. The point in contact with the spring must go up. What do I mean? The spring will now be stretched even further because this point, again, get this part gets to be pulled down. As this gets to be pulled down, this part gets to be pulled upwards. And as this part gets to be pulled upwards, the spring now gets to be stretched even further, meaning that if it was in tension now it gets to be in tension even more. I hope you guys are getting that. Now it gets to be in tension even more. Now, what we'll do is we now have to find the force that will be associated to this extra stretch that occurs. But our approach here will be by looking at what is happening to the spring. You see, what we know is this. The spring has been stretched initially when it was when this beam was, the armature was in contact at A, the spring was only up to this level. And we know the force which was in the spring. But once the circuit is switched on, of course, that is when this happens, determine the force in the spring when the coil is energized and attracts the armature at E. So it's the attraction in the coil here that pulls this armature downwards so that it detaches here. But the detachment now implies that the spring gets to move up. So as the spring gets to move up, in other words, it's like the spring gets to stretch. Initially, the spring was only up to, let's see, which part is that? Yeah, initially the spring was only up to this level, but now we are seeing that the spring has been stretched upwards and now it goes up to that level. So there is some change in the length of the spring, or we see the spring has stretched by that much. Now, what happens in this case? Well, we have to know exactly how much the spring has been stretched. Mostly when you're dealing with Hooke's law, they will give you maybe they'll give you the extension itself and ask you what is happening in the spring. But in this case, we've been given a way of determining exactly what is happening or exactly what that change in X is. Then we use that change in X to find what the force is that could have caused that extension. Now, how do we do that? Well, we have to go back to our diagram and observe one thing. Okay, let me just use lines so that it will be easy for us to see. This was the original state of the beam ABC. I hope that's ABC. I'll just exaggerate everything so that it's easy for us to see. Then after the circuit has been energized, we see that when the armature detaches itself from point A, ABC now gets to be horizontal. The spring now, we're saying the spring now gets to stretch by this much from here all the way up to there. It's this that we're trying to determine. This is the change in the length for that spring or the extension. But observe that in our question, they gave us this from here up to here. In fact, when we're calculating moments, I think we did get what that was. This looks a little bit bent. Can we do better with the diagram? Let me see if I can try to draw it a little bit better. Okay, nothing good. Better, I'll go with that. Okay, so this is what we have there. Okay, so yeah, something like this. Okay, now the extension for that spring, that is this one here in yellow. So this is our change in X. Now, if we go back to our question one more time, what you see is you observe that the distance from here to here, this was given as 30 millimeters. Now, for this part, we have no use for this part. If we are to check again, you will see that that is 50 plus 50, which is 100 millimeters. And then we had our point E somewhere there. But all we're interested in is what this part is. If we go back to the diagram, the angle between the horizontal and AB, that angle there was given as 10 degrees there. So because we know that angle is 10 degrees, we can easily come back to this and say the angle here is 10 degrees. If that angle there is 10 degrees, it implies that even this angle here has to be 10 degrees. Since the angle there is 10 degrees, notice that we can now use tan to find what that change in X is. Because by tan, we have tan 10 degrees has to be equal to the opposite, which is change in X, divided by the adjacent, which is 30 millimeters. No need for the units, just keep in mind that since the 30 is in millimeters, whatever value for change in X you find will also be millimeters. This implies that change in X will be equal to 30 tan 10, and this will be in millimeters. What will be 30 tan 10 degrees? What are you finding there? Someone try this. Okay, so we have 5.289 millimeters. So you guys can verify this, but that is what Michael has given us. So now that we have the change in X, we can now use this change in X to figure out what is happening in the spring. Well, to now determine what is happening in the spring, we can now forget about everything else and just focus on the spring itself. You see, to the spring, what are we seeing? To the spring now we're saying that, okay, this is its state currently. This is where it is. But initially it was somewhere here. This is where it was. So we can now try to figure out a force that could have caused that extension. Well, under Hooke's law, we know to say the extension of the spring, change in X, which is our change in X now, is proportional to the force causing the extension. So the extension in the spring is going to be proportional to that extension. Now, in this case, it then implies that the extension, of course, when you bring in that constant of proportionality, which will be the stiffness in this case, Hooke's law can be seen as the force, the load causing the extension, to be equal to the spring constant multiplying the extension itself. But when you look at the value of K that you've been given, K is given as 120 newtons per meter. So it implies that the change in X as well must be meters. This then comes out as the force is equals to our spring constant, Newton per meter, multiplying the spring, the extension. We found 5.289 millimeters, 5.289. We just convert this to meters, which is by 10 to the power minus 3 in meters. So when you multiply these two, what do you get as your force in the spring? Okay, so here we get 0.634 newtons. So once we have obtained the force, what does this then imply? Well, when it comes to the state of our spring, what is our conclusion in this case? What do you guys think? Are we going to say that this is the force in the spring in this case, or what? Well, what you have to get here is that initially the spring was stretched already. The spring was stretched, implying that we had a restoration force inside the spring, and that force was determined to be that it was 4/3 newtons. You see, what this implies is, at first, the spring was stretched from its rest position to this position here, to this position. And the force that caused that, we'll call that Fs, the first one. And we found that as 4/3 newtons. Then in the second part, the question now says the spring stretches even further, because for that armature to become horizontal, the spring had to stretch even further. So what do we see in that case? The spring now had to stretch all the way up to here. The force that we calculated, which is this one, 0.634, that force, if you follow Hooke's law very well, it is proportional to the extension that is happening. And to find this force, we only looked at the extension from this point coming up to this level. So we can now assign this as Fs2. To now determine the force that will be associated with the extension of the spring all the way from this level going up to when the armature will be in the horizontal position, you would have to now add the force that caused that change in x plus the force that was holding that spring in that state in the first place. So my point is, to determine what the state of the spring would be in this position, you'd now have to say, okay, my overall restoration force in the spring when the armature is at rest or when the circuit is energized, you then have to add the 4/5, which not 4, but 4/3. The 4/3, which was the initial tension inside the spring, plus the additional tension that resulted in that, the change in the position for that armature as it was becoming horizontal, more tension was being added. So this is how you get the final answer of what is happening in that spring. And this, of course, would be newtons. A good example that I would give you to just understand this very well is when it comes to beams. If you had a member that is more like this, and we argue that this member is in tension, and the force inside the member is, let's say, 100 newtons. Now, somehow the member experiences more force, causing it to go in tension even more. If it experiences an additional force that more like tries to stretch it more, it means that the member will be in tension even more. Then the force inside the member, the internal force, will have to increase. But of course, for these beams, in most cases, we don't talk about them. They do extend or stretch, but in most cases, for these solid objects, the extensions are very, very small, because if they did stretch too much, the risk of breaking would be just too much. But for a spring, it's easy for you to track when it expands or when it stretches or when it is actually compressed. But it's the same logic here. Is this clear? What have you found for the final answer, addition of this? What are you finding there? Is it like 1.96 or something? Oh, great. So we have 1.96 newtons there. So this becomes the overall force inside our spring when the circuit is energized. So this is how you were supposed to answer this question. Any question?